first, thank you everybody for attending our talk today called Deep Dive into an ICS firewall. But before we start, let us introduce ourselves. So I'm Julien Lenoir. I'm a member of the security evaluation team of Airbus, where I do evaluate both IT systems and embedded systems, and I do mostly reverse engineering and vulnerability research. And I also have to admit that Linux is my kryptonite.
Hello everyone, I'm Benoît Canrodon, and I'm also a security evaluator working in the same team as Julien. My day-to-day job is to mainly perform embedded system audits and pen tests, and my main interest is everything that is related to Linux and the network. And for the guys in the back of the room, I'm not small, it's just very tall.
Okay, so Benoît and I are not really ICS specialists, but rather evaluation specialists. So today the purpose of this talk is to share with you the results we have along with the methodology we used. So this presentation will be about the evaluation of a firewall which is dedicated to protect industrial systems, and it's called the Tofinoxenon. It's manufactured by Belden. So all the vulnerabilities you will see today were responsibly disclosed to the vendor, who has issued a firmware in November 2017 to fix the vulnerabilities. And 3 of those vulnerabilities were assigned CVEs, and we'll detail them later in this presentation. So today's presentation outline will be the following. So first we'll describe the threats and constraints of the ICS environments. Then we'll present the Tofinoxenon, the firewall we have evaluated. Then the evaluation objectives we had, the guidelines we followed, and also the methodology we followed. Then the preliminary work we had to achieve to get to the internals of the equipment to conduct the evaluation in the proper conditions. Then the evaluation results, and finally we'll conclude. Okay, so first, what do we mean by ICS systems? So we'd say that's everything that is controlling industrial processes. So there are many kinds of industrial control systems. They are categorized by the Purdue model in 3 different categories for 3 different levels, from level 3 to level 0, where the closer you are, the lower the level is, the closer you are from the industrial process. So what's important for you to keep in mind here is that the firewall we have evaluated is meant to be deployed between level 2 equipments, like HMIs or SCADA, and level 1 equipments like PLCs. So first, a few figures regarding the vulnerabilities which were identified in 2017, figures from Kaspersky Lab ICS CERT. So we can see that 322 vulnerabilities were identified, and roughly 60% of them had the CVSS score higher than 60%, which means that they were quite severe vulnerabilities. We can also see that the sectors affected are crucial for our day-to-day lives, which makes this topic very concerning. What's also concerning is that those systems tend to be more and more connected to the outside world. So one of the main constraints of the ICS systems is availability, and there's a very good reason for that. First, because malfunctions of those systems can have significant impacts for people working in the fields there, but also that the downtime costs of those systems are very high. So here we are facing some kind of dilemma, because on one hand you have some systems who are running which are vulnerable. Sometimes they are quite old and fixes are not available, and even when they are, you have very rare occasions to stop the system and to apply the patches. And on the other hand, there are those systems face threats, and real-world attacks do happen, and we saw them in the Triton talk this morning, which was a good talk, by the way. So to answer this dilemma and this this business need, dedicated systems have come to the market, which are meant to be deployed in front of vulnerable ICS systems, and they are meant to stop the attack by filtering network packets and to ensure that only valid packets reach potentially vulnerable equipments to protect them, and invalid packets are meant to be dropped. Whoops. So our objective, we had two objectives here. The first one is kind of obvious. We wanted to answer the question: how effective are this equipment to protect the ICS systems? And the other one is there any vulnerability inside the firewall itself that may be introduced in the network by deploying it? So we had a few constraints. The first one, which is the very important one, is that we were not allowed to physically tamper with the equipment, which means we were not able to open it and unsolder the flash, for example. So we were limited to software-only attacks. And we had, I would not say limited, but we have a few inputs, which were firmware updates available from the vendor website, the user guides, and of course the appliance itself to play with it. So our approach was the following. We first listed all the features that the equipment has. Then we took in consideration the French Network and Information Security Agency security profiles for this kind of ICS firewalls, and we'll detail them later. And finally, with these profiles, we kept all the most relevant and the most relevant features, and we had the list of those which had to be evaluated, and then we evaluated them the offensive way.
Okay, so now we are going to present the Tofino Xenon system from a final user point of view. So it is a firewall, so it has to be located in front of your ICS, of your network of ICS. It will physically segregate the open world that is represented by the control network, that's where the attack comes from, and the secure zone that is containing your ICS systems. But from a logical point of view, it is free transparent and has not even an IP address, meaning that if you buy a Tofino Xenon system, you do not have to change your network configuration, you do not have to change your network addressing. It has been designed to be fully plug and play and to have the least possible impact on your existing system. Now the filtering is done at two different levels. A first classic one, which is based on network parameters like protocol, port, destination, source, and a more ICS-oriented one, where the Tofino system will deeply inspect the content of the application layer of the ICS packets, and according to the content, it will allow or not the packets to go through the firewall. There are three different protocols that are handled by the Tofino appliance: the Modbus TCP protocol, the Ethernet IP, and the OPC Classic. As Julien said previously, a very important thing in ICS environment is the availability. And for that, Tofino developed two different modes for the appliance. The first one is a test mode, where packets that should have been dropped are only logged and not really dropped. And once you are in line with your configuration, you can switch to an operational mode where the packet will be really dropped if they do not match a firewall rule. Now I'm going to describe the two main components of the Tofino. The first one is a security appliance, the small box that you will install in your network. So it has been physically designed to fit in a safety critical environment. And the box has two Ethernet ports, one for the open zone and one for the secure zone connected to your ICS systems. There is also a USB port that is used to push filtering configuration, to push new upgrades, or to retrieve some log of the appliance. Now, there is also the configurator, which is the software part. It's the only official way to configure one or more appliance. It's a Windows-rich client, and it allows to define the filtering rules, to customize the DPI level for ICS protocols. And once you are in line with the configuration, you have two different ways to apply this configuration. The first one is using the network protocol that has been customized by Tofino and that we will describe in a few slides. And the other way is to generate an encrypted file that you can store in a USB stick.
So now a bit more about the evaluation objectives, the guidelines we followed. So in those guidelines, they make a few assumptions. The first regarding the ICS firewall equipment. The first one is regarding its locations. So they consider it's not necessarily stored in a location where there is a strict control access, which means that an attacker may have physical access to the equipment for a few minutes. Also regarding the dimensioning of the equipment, which means that it's properly dimensioned for its task. In other words, that floating attacks are not relevant. And also that an attacker can purchase the equipment to search for vulnerabilities prior to launching the attack. And with this regard, what Benoit and I did during this evaluation is very representative of this kind of attacker profiles. So as I said, the attacker can have an access for a few minutes to the equipment, but it's considered that it cannot open the box and perform physical attacks on the equipment. So the security objectives, we summed up all the security objectives that are described in the guidelines, and we kept those are very relevant for our equipment. So the first most important security objective, I would say, is the firewall security objective. So first, policy enforcement, like what's the basic firewall functions, and also protocol conformity analysis, which is the packet inspection. Also the administration, because we consider that it must have secure authentication and also proper access control to the equipments on both USB and network in our case. And also on the upgrade, because we consider that the upgrades the firmware must be properly signed on both, here once again, on both USB and network firmware, because both can be uploaded both ways. So now the preliminary work we had to achieve to get to the internals of the equipment. The way Benoit and I work is the following. We usually like to have access to the code of the equipment, either the source code when it's available or the binary code of the firmwares to do reverse engineering. So we tried this approach, but unfortunately for us, the firmware are fully encrypted and the decryption keys are stored inside the appliance. And this appliance was kind of a black box. So, and as I said, we were not able to unsolder the flash to extract the decryption keys. So this way was a dead end. So we looked at the way the USB configuration is applied, but as Benoit said previously, it's also encrypted, and the decryption keys are also stored inside the appliance. So this was a dead end too. So the last way of doing for us was with the custom protocol that the configurator uses to configure the appliance. So what we did, we reversed engineer the configurator to understand the packet format and the crypto scheme that is used to authenticate and to administrate the security appliances. That's what I'm showing you right now. So as Benoit said, the appliance doesn't even have an IP address. So there must be a way for the configurator to know where is located the appliance inside the network. So basically and that's the purpose of the discovery protocol. So what the Tofino did is that the configurator is sending a piece of data here to ICS systems, and as the appliance is standing somewhere in between the ICS systems and the configurator, it will see the packet coming. It will intercept this packet. This packet contains a piece of data encrypted with a key, KH, where H stands for hard-coded, and this key is hard-coded in both the appliance and the configurator. So The appliance receives this packet, decrypts the data, and if the data inside this packet is meaningful, it means that the appliance knows it's being discovered and answered, acknowledges the discovery packet. Then the configurator knows the appliance is standing somewhere here on this network path, so it's now sending an authentication packet with another piece of data encrypted with 2 other keys, K2 and K3. Those keys are not hard-coded, but shared between the appliance and the configurator. So when the appliance receives this packet and manages to decrypt the packets, it knows it's sharing K2 and K3 with the configurator. This way it authenticates the configurator, and so it opens an SSH port for the configurator to connect to it. So what we did basically, first we reverse engineered the protocol to understand that, and we also implemented our own version of the client in Python. We extracted the default keys, K2, K3, and also the SSH key to implement our own client in Python, and we are able to open and to connect to the appliance with over SSH. So we got a root shell because on the appliance everything is running as root. It's unfortunately it's still quite common on the embedded systems. So this was a major step forward for us because from now on the appliance was not anymore a black box. So we understood that it was a Linux operating system running on top of a PowerPC architecture, and we had access to the whole file system content, the internal configuration, the API table rules, and we were also able to do live debugging to understand how the appliance works. So now we are moving to the evaluation part where we've evaluated all the features and to see if the security objectives are met or not.
Okay, so now when you first install a Tofino appliance on your network, you can use any configurator in order to connect and configure it, because by default, every appliance are sharing the same default keys. So the first thing that you will want to do is to restrict this access to your configurator and not the other ones. This phase is called the association phase. It consists in generating new keys on the configurator and send them to the appliance. Once this association phase is done, you are the only configurator that is able to connect to the appliance, because the knowledge of K2 and K3 is mandatory in order to do the authentication part of the protocol. However, your appliance can still be discovered by other configurators because the discovery part is using the KH key, which is not changed during the association phase. So we have audited the code that is doing this custom protocol, and we didn't find any vulnerability. So for us, it means that the network authentication objective of the Tofino is met. Now, what about the Tofino upgrade mechanism? It can be done using 2 different ways. The first is to use the configurator and the network protocol. It is well designed and well implemented. And the other one is using a USB stick. A USB update is in fact a zip archive containing 2 different files. The first is an update script, and the second one is a data file containing a Linux kernel and a file system. Both files are encrypted using the AES algorithm, and the key used for encryption is shared among every appliance. But at the very beginning, we didn't know this key, so we were not able to decrypt the firmware. But once we get the shell access on the appliance, we were able to extract this key and then to decrypt the firmware. But the major issue here is that only the update script is signed and the data file is not signed, meaning that if you modify the data file, the Tofino system has no way to know that an unauthorized modification has been applied. So, when you first plug your USB stick in order to upgrade the Tofino, it decrypts and checks the signature of the script, and if it is correct, it executes the script. The script then decrypts the data file and write the Linux kernel and the file system into the Tofino flash memory. So an attacker can connect to the Tofino website, retrieve a valid firmware, decrypt the data file because it has access to the keys that is shared among every appliance, change the content, for example, to backdoor the Linux kernel, to change some binaries in the file system or whatever, re-encrypt the file, and then store it in the USB key and plug it into the Tofino. The Tofino won't have any way to know that this firmware has been modified. So, if you are an attacker and if you have a physical access to the appliance, it's game over. If you are able to plug a USB stick into the appliance, it's game over. The impact of the appliance is a full compromise. And so, our security objective about the firmware signature is not met because the data file is not signed. So this bug was reported to the vendor, and a CVE has been assigned, and it was patched in the latest firmware. Now we are going to describe the firewall internals of the Tofino appliance. So because the underlying operating system is Linux, without any surprise, the filtering is done using NetFilter. NetFilter will do the filtering using network parameters, but it is also responsible for forwarding packets, for forwarding ICS packets to 3 userland modules, one for each protocol that is handled by the Tofino appliance. Those modules have the responsibility to parse, analyze, and according to some rules that we will describe later, to say if the packet is allowed or not to go through the firewall. Okay, so now I'm going to describe a quite tricky bug that we will use in our final attack. But first, I need to detail what is happening when an administrator wants to enforce the DPI filtering while there is already established ICS communications. Let's take an example. You are an administrator. You have installed a Tofino appliance on your network. It is in test mode. You are in line with this configuration. The logs are saying that everything is okay, so you want to switch to operational mode to really drop bad packets. But at the same time, in your company, you have an HMI that is communicating with a PLC. When the PLC will send its response, and when the administrator will push the button in order to really filter the packets, the PLC response may be dropped because it is not yet related to a tracked connection. And in an ICS environment, availability is crucial and it must not happen. So, to avoid this problem, Tofino developed a workaround that allows for 30 seconds when a configuration has just been applied, they allow every ICS response. And for that, they implement a custom kernel module, a custom NetFilter module that is adding a kind of time to live parameters to firewall rules. And those rules that we have called timed rules, when they are applied, a timer is started. And they match packet only if the timer have not expired. So if we come back to our case, when the PLC will send its response, the packet will be allowed, not because it is related to a tracked connection, but because it is in the 30-second time frame. It's a compromise between availability and security. But because it's a compromise, it means that for an attacker, it's a window opportunity for 30 seconds to bypass the firewall, to bypass the classic firewall. So the impact is high because you have 30 seconds just after applying a configuration to bypass the classic filtering, but the impact is quite low because it only happens when there is a new configuration. However, even if you can bypass the classic filtering, the deep packet inspection still applied on your packets. Keep in mind this problem because we will use it in a few slides.
Okay, so Benoit showed you the path of the network packet through IP table rules to DPI modules for filtering. So now we will talk about what those DPI modules are doing, because that's the real added value of those equipments and that's the core of their technology. So they are doing deep packet inspection at two levels. The first one is at packet format. So basically what they are doing is that they are ensuring that the packets we are meant to go through the firewall respect the specifications and they are well formed. If they are not, they will be dropped to avoid any parsing error on ICS equipments and triggering any vulnerability. That's the first level. The second level is content filtering. Modbus and Ethernet IP have a master-slave model where the master sends commands and expects response. And those commands are actions you want to perform on the target equipments, like reading memory, writing memory, programming, and things like that. So the firewall has the ability to restrict the set of commands that are allowed inside the packet, even though the packet format is correct. So now I will show two examples of this filtering. So the first one is the packet format filtering. Is an example, an extract from the Modbus specification, and that's just an example. So the function code number one is a command to read data from the equipment. So there are 1 byte for the command, 2 bytes for the address where we want to read from, and 2 bytes for the quantity of data we want to read. So the DPI module will basically add the address and the quantity to check if there is an overflow, and it will also ensure that the quantity is below the maximum authorized by the specification. So that's just an example. There are many of those kind of checks in the modules. The other one here is that the content filtering, that's the restriction on the allowed commands. So from the Tofino configurator, Benoit has talked to you about a few slides ago, you have an interface when you can apply predefined profiles to say I want to restrict to read-only commands, read-write, etc. And you also have an advanced menu when you can cherry pick which commands you want to allow or not. So now I will describe all of the filters, the 3 filters we have audited, starting with Ethernet IP. So this is only on one slide. It will be very quick. We had to make decisions regarding the time we had. So Ethernet IP protocol is running on top of TCP or UDP, and it's conveying control industrial protocol CIP messages. So we found a bug here, but unfortunately for us, as an attacker, it's only on the on replies, meaning from slave to masters, because from slave to masters, the modules are also doing the packet inspection. So in fact, it was an out-of-bound write inside in the DPI when it's parsing the packets, but we were not able to use it for code execution or memory corruption inside the filter's memory. We just used it to bypass the sanity checks, the packet sanity verification that are done on the reply messages. So this was reported and patched by the vendor, but we didn't ask for a ECV number on this one. So just for you to know that we also audited this module. Now we're moving to the Modbus filter, which is the results are slightly more interesting. So the Modbus commands or function codes are conveyed inside the application data units. You have an example here on the screen. So it's composed of a header and also a protocol data unit, which contains the function code you're sending to the equipments, along with the data, and the format of the data depends of the function code you're sending. What's interesting to notice here is that the length of the protocol data unit is stored inside the header. So the first thing we noticed is that the Tofino allows packets that contain multiple application data units inside the network frame, even though this is not explicitly defined inside the Modbus standard. And it's really interesting. So what's the filter is doing for each the application data unit? So it will check whether the function code is authorized regarding the profiles that are applied, and also that the sanity checks are correct. So all the sanity checks on the first will ensure that the application data unit length is below the above the minimum and below the maximum authorized by the specification, with 7 and 2048 bytes. And they will also do sanity check on the data that are specific to the function code. But they missed here a very important thing. They didn't check that the length stored inside the header is below the maximum authorized by the standard, the 2048 bytes. And that's very important. So now let's see what's happening when the filter is validating a packet which contains multiple data units. So it will first, it's done in a loop. You have the pseudocode of the loop implemented inside the filter here. So the filter is first checking that the first application data unit is correct. If it's correct, it will use the length stored inside the header to compute the offset of the next data unit. And then it will do the check again on the next one. And it will do it in a loop. And at the end of the loop, if all the data units are correct, the frame is considered valid and can go through the firewall. But what happens in case of an invalid length is conveyed inside the first application data unit header. So the first data unit is checked, so it has to be correct to go through the firewall. Then it will, the filter will use the incorrect length from the header to compute the offset. And the funny thing here is that it will see that something is going wrong. So it will exit the loop. And at the end of the loop, it will do another check. And here is there is a logical issue because even if the size is incorrect, it returns frame valid instead of frame invalid, which means that we'll stop the verification and we allow the frame to go through the firewall. And that's a major issue, but still we have to have the first application data unit that is correct. And for that, we in our test we chose the function code number 7 here because it's a only 1 byte PDU and it's in all predefined predefined list of allowed comments. So and as we can see on this packet here, if the first data unit is correct, with the packet containing arbitrary data can go through the firewall. So that's as I said a major issue because it's kind of a universal bypass of the Modbus filter because this way we send the packet which contains an invalid length and also arbitrary data across the firewall, and it can have an important impact of the ICS system. And it's exactly the kind of thing the firewall is meant to protect us against. So the security objective of the Modbus filters regarding conformity analysis objective is not met. And this bug was assigned the CVE and was reported to the vendor.
Okay, now we are going to describe the OPC classic filter, which is filtering OPC protocol. This protocol is based on Microsoft COM-DECOM technology and has the specificity to use multiple TCP connection using dynamic ports. If you have a look on the diagram below, so when the client opens a TCP connection on the static port 135, after a while the server will ask the client to use a new TCP connection. And this new TCP connection will be done on a port that is inside the application layer of the packet. So when the client receives this packet, it opens this new connection. But of course, this new TCP connection has to be allowed by the firewall, and you can't guess the dynamic TCP port, so it is the responsibility of the OPC filtering to pass this kind of packet and to dynamically add this rule to allow the new TCP connection. It's exactly what is done on FTP with the FTP data connection. But there is a bug. When the OPC filter is passing the packet, it is not checking the state machine, meaning that if you are the client, you send a request and you can send a response to your request. The OPC filtering is not checking if the response is coming from the PLC. So you can send the request and the response. And the consequence will be that a new filtering rule will be added, allowing a connection from the PLC to the attacker, which is not the most interesting for an attacker. So the impact is quite low, but what is important is that you can, as an attacker, dynamically add a rule whenever you want, and it will have some very interesting impacts in the following slides. Another vulnerability that we have found on the OPC filter is the way that the filter is handling small packets. OPC header is composed of 19 bytes, and if the filter received a packet smaller than 19 bytes, it considers this packet as invalid because too small. But there is a logical flaw, as you can see on the right side of the slide, in the pseudocode. The return value is set to 1, and the parsing is done only if the size is greater than 19. And if it is not the case, the packet is not parsed, but the return value is not changed. You are never going to the else branch. So this invalid packet will be allowed to go through the firewall. And unfortunately, OPC protocol is on top of TCP, meaning that you can use TCP fragmentation. You can take a big bad packet, split it in very small packets, send every small packet to your target. The OPC filtering will allow all these small packets to go through. And when the target will receive all these small packets, it will reassemble everything to get the big bad packet. So using TCP fragmentation, you are able to fully bypass the deep packet inspection of OPC protocol. And so the OPC protocol conformity is not met because of this flaw. Now we have seen many low impact or low potentiality bugs. We will try to put it together in order to get a higher impact on the firewall. But first, I will just do a brief summary of findings that we will combine. The first one is the time rule vulnerability that allow you to bypass the classic filtering for 30 seconds, but only when a configuration is applied. The other one is the capability for an attacker to dynamically add a firewall rule. And the last one is the one that I have just described, is the capability to bypass OPC deep packet inspection by using TCP fragmentation. In addition to this bug, the Tofino developers were not aware of a very specific netfilter behavior. When you add a rule in netfilter, this rule is added to a set of existing rules. Meaning that if you add a rule, every rule will be applied again, including timed rule. And when a time rule is applied, the timer is reset. So the potentiality of the time rule vulnerability was low, but in fact, because of this very specific netfilter behavior, it happens if every time you add a rule. So whenever the attacker wants. But there is still the deep packet inspection that is done on this packet, but you can bypass it using TCP fragmentation. So in this slide, I will describe the different steps in order to run a complete attack for bypassing the filtering of the Tofino firewall. We use a Linux target with an open telnet service. This telnet service was not allowed by the firewall. The only thing that was allowed between the attacker and the target was the OPC protocol. So you first have to open an OPC connection on a static port 135, then send a request and a response to your target telling the target that you want to use a new TCP connection on a new dynamic port. When the OPC filtering will pass this packet, it will add the rule, and the consequence will be that every rules will be applied again, including time rules, so the timer will be reset. So you have a 30 seconds opportunity to bypass the classic filtering and to open a TCP connection on your telnet service using a source port matching the OPC service, just to be interpreted as an ICS response. And finally, send fragmented data to use the telnet service. In conclusion, if OPC filter is enabled between two devices, the whole filtering, the whole Tofino filtering can be bypassed. This was patched in the latest firmware version, and a CV has been assigned to this bug.
Okay, so we've been through all the security objectives of the equipment, so it's now time for us to conclude regarding this evaluation. So what we can say that before trusting any security products, we have to perform a deep evaluation of the product, and following a known and recognized referential or guidelines is a very good idea. For example, Benoit and I were not ICS specialists, but following this INSSI guidelines helped us a lot. What we can say regarding the Tofino case, so there are good points. They use open source and reliable components. Their design is quite modular, which means that when you have a vulnerability inside a DPI filter, you can patch it quite easily without costly modification to your software architecture. That most of the vulnerabilities are implementation issues, that the Modbus bug here is a very good example of that, because instead of returning, if they patch the return 1 by return 0, the bug is not present anymore. And what's also very interesting is that the very good reaction of the vendor regarding responsible disclosure, because we had a very constructive dialogue with them. They were very responsive. They did not try to minor the impact of the bugs, and they were very, 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 very good. There is still room for improvement, though, because as we've seen that everything is running root, and I think it's still the case. So there is still lack of hardening of on the operating system. So now we've done the evaluation, so we know the limitations of the products, and we could deploy it safely after applying the patches. But if we take another step back and think about what could be the takeaways of this presentation, so the first one is that architecture, safe design, risk analysis, and those things are crucial, because without those, you will never end up having a secure product. But still, you do have to check the implementation, because minor bugs can bring your security down. And that's things that Benoit and I see every day in our internal evaluations. And the good way for checking this implementation is doing a deep evaluation of the products, which means we have to spend time on it, because that's the only way for evaluators like us to find the tricky bug. And I'm thinking about the time rule vulnerability and the custom kernel module. This one was really tricky. And finally, I have to say that the most interesting attacks usually come from the combination of multiple bugs that, if they are taken separately, they would seem to have a very low impact. But when you put all them together and you chain them, you end up having a very significant impact and very interesting attacks. And the OPC filter bugs Benoit I've presented you is very, very good example of that. So now that's the end of this presentation. We want to thank our colleagues at Airbus for their support. We want also to thank the vendor, because they were very positive about us speaking here at Black Hat, and we know it's not always the case. And of course, thank you very much for listening to this presentation, and we sincerely hope that you enjoyed it. Thank you very much.